ME204, planar kinetic equations of motion. That's the Newton's law stuff, F equals ma. And we're going to deal with rotation about a fixed axis. Here are some inspiring scriptures if you're feeling a little bit discouraged about now in the semester. 2 Corinthians 4:8-9. We are troubled on every side, yet not distressed. We are perplexed, but not in despair, persecuted, but not forsaken, cast down, but not destroyed. How is that possible? Well, with faith in Christ, that's why it's possible to be troubled on every side, but not distressed. Moroni 7:41. What is it that ye shall hope for? Behold, I say unto you that ye shall have a hope through the atonement of Christ and the power of his resurrection, to be raised unto life eternal, and this because of your faith in him according to the promise. Doctrine and Covenants 101:16. Therefore let your hearts be comforted concerning Zion, for all flesh is in my hand. Be still and know that I am God. I can guarantee that if you will put in the effort, the correct effort, not just plugging and chugging equations to complete assignments, but if you really do put in effort to truly understand concepts, it'll save you time in the future, it'll make your education more enjoyable, and you will remember for the long term these concepts. Newton's second law. For translating objects, that's F equals ma, and in plain English, an unbalanced force will cause a mass to accelerate. And mass is simply a measure of an object's inertia. So mass is an inertial measurement. So a force will cause something with inertia to accelerate. That's what this F equals ma means. For a rotating object, what causes a rotating object to speed up or slow down? Well, it's a torque. A torque will cause the rotating object to accelerate, to speed up or slow down. So what is this inertia property? Well, that's what we've been learning about, this mass moment of inertia, or what we call the second moment of mass. So this m equals I alpha, that is the Newton's second law for rotating objects. Here's an example of how we might approach a problem like this. Here's a drum, has a mass of 60 kilograms and a radius of gyration of 0.25. We're going to neglect the mass of the cord, and we're going to attach a 20 kilogram mass block. We're going to release it from rest and determine the angular acceleration. First of all, we probably need to make logical sense out of why in one place it's saying the radius is 0.4 meters, and another place it's saying 0.25 meters. Well, that's because they're quoting a radius of gyration, which is an equivalent radius, or a place where we can assume that all the mass of that pulley is concentrated so that we could easily compute the moment of inertia. If I know the radius of gyration, I can compute moment of inertia just by this second moment of mass equation. So there's the moment of inertia of that drum. Now let's do a free body diagram. I'm going to do just the drum for now. There are some of the forces on the drum. And notice I'm leaving the tension in the cord as an unknown. Hopefully you're not tempted to say that the tension in the cord is equal to the mg of the block. That's not true. If the tension in the cord was the same as the weight of the block, then the block wouldn't move. It would be a balanced force. So certainly the tension in the cord is less than the weight of the block. Let's look at the kinetic diagram. Well, the only acceleration we'd have would be the rotational acceleration of this drum. And we have to remember that it's the forces that cause the accelerations to happen. So we're going to sum moments about g, or 0.0, and we're going to set that equal to the accelerations about 0.0. And there we have one equation but two unknowns. So let's take a look at another free body diagram. Let's look at the block itself causing this acceleration to happen. We can sum forces in the y, that would be the ma. Now we have another equation, but we've added another unknown. So now we have three total unknowns, but only two equations. But we can recognize that the acceleration of the block is related to the alpha of the drum by the radius, this A equals alpha r. That was from chapter 16 that we've already discussed. So now if we solve simultaneously those three equations, three unknowns, we'll find the tension in the cable, we'll find the acceleration of the block, and the alpha of the drum. What if the object's not rotating about its center of gravity? Well, if O happens to be a fixed axis, we could simply sum the moments about O and make sure that we use the moment of inertia about that point of rotation. Now, here's a caution. This is only valid if point O happens to be a fixed axis. So remember that. This is only valid if point O happens to be a fixed axis. Let's take another example. This rod has a mass of 5 kilograms, is supported by a pin at O and as well as a cord at A. Let's determine the reaction force at O before the cord is cut and the reaction force at O after the cord is cut. Before the cord is cut, that's just a statics problem. Let's do a free body diagram, and we don't need a kinetic diagram because it's just statics, we have no accelerations. Sum of the forces in Y, and we can do sum of the moments about O, and solve simultaneously. We find that the reaction at O is 32.7 newtons. Now let's take a look at what happens after the cord is cut, or the instant that the cord is cut. We'll do a free body diagram. We can do a kinetic diagram, and this is one of the possible kinetic diagrams. And notice, since O is a fixed axis, we can do a parallel axis shift on the moment of inertia and say IO alpha. So let's compute that IO using the parallel axis theorem. And now we can sum moments about O from the force side, and that will be equal to the IO alpha on the kinetic side. And we could directly find alpha of the rod. But that's really not what we were looking for. We were looking for FO, the reaction force at O. So this setup with that kinetic diagram that only shows IO alpha wasn't very helpful. Here's another kinetic diagram that is probably a little more helpful. Now we're thinking in our mind's eye that the object is rotating about G and that G happens to be accelerating as well. So we're ignoring this fixed axis, and we're looking at just this general plane motion where the object is rotating and translating both. Now notice if G is moving, we have the tangential component of acceleration as well as normal component. But the instant the cord is cut, the omega is 0, so the normal acceleration at that instant is 0. So in this case we're only dealing with the tangential acceleration as well as the alpha. So now let's sum moments about G, and that will be equal to IG alpha. There my reaction force starts to appear in the equation. And alpha, since I've already found it to be 20.9 radians per second squared, I use the moment of inertia of 0.27, and that's the moment of inertia about the center of gravity, and I can find that FO, the reaction force at O, is 28.2 newtons. So this might be something interesting to ponder. Why does the reaction force at O go down after the cord is cut? Now if you're truly interested in learning, you're going to pause the video and you're going to ponder about that and see if you can develop some intuition about this. So there are actually two options when we have something that's not rotating about its center of gravity. One is if it happens to be a fixed axis, we can sum moments about point O as long as we're using the moment of inertia about that point of rotation, point O. But remember, that's only valid if O is a fixed axis. Another option is we can sum moments about any point, including point O, as long as we take the kinetic moments about that same point. That's what that little script M is. It's the moments on the kinetic side of the diagram. And that could include I alpha as well as any MAs times the distance. So what are these kinetic moments? Well, we're already familiar with moments of mass, moments of force. Why not kinetic moments? That's the moments of the MA. So this script m is a kinetic moment, and that's simply all the moments on the kinetic diagram. And the kinetic diagram shows the I alphas as well as the MAs. Now notice, if it's MA, I'm going to multiply it by the distance to make it into a moment. And the I alpha is already in moment form. So let's do another example using this kinetic moments and see if it's a little more streamlined. It makes the calculations a little more streamlined. This is the same problem as before, but we're going to approach it a little bit differently. First we'll find the IG, and let's do a free body diagram. And notice this time I didn't cut through the chord for my free body. I'm doing the whole system, the free body on the entire system. I have the mg of the block, the mg of the drum, the reaction force at O. And those forces, somehow a combination of those forces, will cause this kinetic diagram to happen. I'm going to have the block accelerating downward and the drum accelerating in a rotational sense. So let's sum moments about point O. And then we'll have to remember that if we sum moments on the force side of the equation about point O, we better sum all the moments on the kinetic side of the equation about point O as well. So on the force side of the equation, there's a moment about point O. It's the mass of the block times g multiplied by the radius. That's the moment about point O. On the kinetic side of the diagram, let's sum moments about point O there as well. Well, I have the I alpha. That's a moment about point O. And I also have the MA acting at a distance r. That's a moment. So notice I've summed moments about point O on both sides, the free body and the kinetic side. Set them equal, and I plug in some numbers, and notice that I have two unknowns, alpha and A, but alpha and A are related, so I can make a substitution and then solve for acceleration, 4.52 meters per second squared. I get the same answer, and this is a little more streamlined. So it's pretty important to understand this concept of kinetic moments. And it's not too complicated. It's simply, if you draw the correct free body and kinetic diagrams, you can sum moments about any point you like, as long as you sum moments about the same point in both diagrams.